We're going to consider a constant coefficient differential equation, linear, second order, and we're going to talk about the case when you've got complex roots for your characteristic equation. So we're going to take solutions of this form, e to the y, e to the lambda t, and when we apply the chain rule and differentiate, substitute back in, we get the characteristic equation that helps us determine the values of lambda. Now we already know that these are going to be given from the quadratic formula, and we've discussed the case when you've got real distinct and real repeated. Now the situation is, well, what happens if this value here is negative? Then what you get are complex valued lambdas. As an example, let y equal e to the lambda t. We'll plug it in. We'll get our characteristic polynomial. It'll look something like this. The quadratic formula tells me that I'll get negative of negative 3 plus or minus negative 3 squared minus 4 to 4 all over 2 times 2. So I'll get 3 plus or minus 9 take away 32 all over 4. So we're going to separate this out. First of all, we'll factor out a negative. 32 minus 9 is going to give me 23. And this term here, the negative under the root, we're going to interpret as the square root of negative 1, square root of 23, which is going to be I into root 23. And that's where the complex value comes in. So the proper way for us to deal with this lambda is to realize it's going to be 3 over 4 plus or minus square root of 23 over 4 I. So really, what happens is we've got one of our lambdas being 3 over 4 plus root 23 over 4 times I, and the other will be 3 over 4 minus root 23 over 4i. These values here are almost identical, save for the sign front of the imaginary part. So these lambdas are what are called a complex conjugate pair. So for second order, you will always have these conjugate pairs. There's no option. How do we write the solutions? If we have e to the lambda t, anytime you do have complex valued solutions, we are going to think of them as coming in pairs like this. Some alpha, which is the real part, plus or minus I beta, which is the imaginary part. And again, those are the complex conjugates. We have alpha plus I beta, alpha minus I beta. So the two solutions, so one of these is going to be alpha plus I beta into t. The other one is going to be y equals e to the alpha minus I beta t. The idea here is that what we need to do is talk about defining an exponential when it has a complex power. We're going to define the complex exponential like this. You very likely have forgotten what the Maclaurin series is. This definition allows us to do the following. If we ever need to take an exponential and there's a real and imaginary part upstairs, we're allowed to split it up into the real exponent and the imaginary exponent. If we ever need to do something like take the derivative of an exponential where there's a real or imaginary number upstairs, a complex number, we can just use the chain rule and everything works out just like it did before. So all of that's fine. What is e to the I beta t? And this is where we use the definition again. All right, so this means 1 plus whatever's upstairs, I beta t squared over 2 factorial, I beta t cubed over 3. Now in this case, I'm going to write out several of the terms because we're going to be looking for patterns. Something that you'll pick up on as a pattern is that I squared is -1, I cubed is I times I squared, which is -I to the 4 is I squared times I squared, which is +1. And then this pattern will keep repeating once we go past that. So I to the 5 is I times I to the 4, which is just an I. And then the pattern keeps repeating after that. When we have e to the I beta t, I'm going to try to group this in terms of things that will produce an I and things that won't. So we'll have 1. The next term is going to produce an I. So I'm going to add this down below. We'll have an I beta t. The next term here, when I square that exponent, is going to give me a negative beta squared t squared, which I can just write like this. Beta t all squared. And remember, the negative is outside, out in front of it. This term, because of the powers that we've talked about here, will be -I beta t cubed over 3 factorial. This term will end up giving me beta t to the 4 factorial. And then if we kept going, we would have I beta t to the 5 over 5 factorial, and then so on and so forth. If we take a look at everything in the blue can be written as a series. It can be written as beta t to the power of 2n over 2n factorial. And in that last one, if we factor out an I, we can group this in the same sort of way, -1 to the n, beta t to the 2n plus 1 over 2n plus 1 factorial. Now, gold star for you if you recognize that this is the Maclaurin series for cosine of beta t, and over here, this is the Maclaurin series for sine of beta t. But this is something very famous called Euler's formula. And it ends up saying to you, e to the I beta t, whatever number is beside the I, just ends up going there, cos beta t plus I sine beta t. Now, more generally, we see it as e to the I theta is cos theta plus I sine theta. If we put in a negative, so e to the I negative I theta, you can think of it as I times a negative theta, cos negative theta plus I sine of negative theta. Properties of cosine say that the negative on the inside doesn't matter, and if you have a negative on the outside of sine, it gets to come out like that. And the reason that we need this is when we solve our dE, so when we come back to our example, we had 2y double prime minus 3y prime plus 4y equals 0. We found that the solutions were e to the 3 over 4t, e to the I root 23 over 4t, and e to the 3 over 4t, e to the minus I root 23 over 4t. Now note, you could show that these solutions are linearly independent. So if you were to take the Wronskian of any e to the alpha plus I beta t, e to the I beta with the negative in the t, you could always compute the Wronskian of them. And you could always show that they would be linearly independent. So if you want to pause the video and go ahead and compute that for fun, you would end up getting negative 2I beta e to the 2 alpha t, which would be non-zero, so they'd be linearly independent, and that would make them a basis, or we call it a fundamental set of solutions. But in practice, we don't use this complex exponential form. We don't like using complex exponentials. What we do is instead we rewrite. And we rewrite this using the Euler formula. So the general solution would normally be, let's say, some constant k1 e to the alpha plus I beta, something like this. And normally you'd say, oh, okay, here is the general solution, I am done. But again, we're trying to avoid using the complex exponential. So there's a way that you can deal with this. You can say k1 e to the alpha t e to the I beta t plus k2 e to the alpha t e to the negative I beta t. Incorporate that Euler formula, you'll get a cos beta t plus I sine beta t. Incorporate that Euler formula, cos beta t minus I sine beta t. And then you can start grouping things in terms of coses and sines. So there's your cos. If you want, you could group them together. You'd have a common factor of e to the alpha t. You'd have a cos beta t. What's key here is that you've got k1 bunches of them from the first one plus k2 bunches of them from the second. Now, if you just wanted to try to group things by sines, you'd have e to the alpha t sine beta t. You'd have I k1 minus I k2. The whole point of the story is that constant plus constant is just some other arbitrary constant. And constant plus constant, it doesn't matter if they're complex or not. This is just some other constant. So your general solution could be written as e to the alpha t cos beta t plus c2 e to the alpha t sine beta t. So then another fundamental set, or a basis, is just e to the alpha t cos beta t e to the alpha t sine beta t. And this is how it works. So when you have your complex lambdas, e alpha plus I beta, your solutions will always simply be e to the alpha t cos beta t, and then e to the alpha t sine beta t. So in the problem that we were working on, I'm now going to turn it into an initial value problem. And let's say that the initial values here are y of 0 equals 0, y prime of 0 equals 1. We already know that if we have e to the lambda t as my solution, we've already found that it's 3/4 plus or minus root 23 over 4t. So there's alpha, there's beta, and there's an I here that I forgot to write. So your fundamental set, you could think of it as e to the 3/4 plus I root 23 over 4t, e to the 3/4 minus I root 23 over 4t. But nobody uses that version. In practice, we don't want to work with things that have i's in them. So the other version of this fundamental set would be 3/4 t cos root 23 over 4t, e to the 3/4 t sine root 23 over 4t. So the beta ends up going in there. So there's alpha, there's beta, alpha, beta. So the general solution is C1 e to the 3/4 t cosine of root 23 over 4t plus C2 e to the 3/4 t sine root 23 over 4t. So y of 0 in this problem is going to be C1 times e to the 0 times the cos of 0, which is 1, plus C2 e to the 0 times the sine of 0. So that whole second term is 0. Y of 0 is C1, which according to the initial condition has to be 0. So that means so far my general solution will collapse down to C2 e to the 3/4 t sine of root 23 over 4t. To figure out what this C2 is, I need the other initial condition, so I have to take the derivative of this. It's going to be messy. I'll have 3/4 e to the 3/4 t times the sine plus e to the 3/4 t 23 over 4 square root cosine 23 over 4t. Now, if my initial condition is given, and it's given as y prime of 0 equals 1, when I plug everything into my y prime of 0, I'll get C2 is 3/4 e to the 0 sine of 0, so that term's going to go away. And then I'll get 23 over 4 e to the 0 cosine of 0, which will be 1. That means I'll have C2 root 23 over 4 equals 1, according to the initial condition. C2 is 4 over root 23. And then the particular solution to this initial value problem is this. 4 over root 23 e to the 3/4 t sine root 23 over 4t. Now, doing a bunch of algebra like this is great, I suppose, but it's much more valuable for us to understand what this solution does. And it will turn out that a solution like this is probably not physically realistic. The initial condition said to us at time 0, we will be starting at a y value of 0. This solution has oscillations. It grows, it oscillates like sine, but it has what's called this attenuation factor. It's going to grow larger and as an exponential curve. So it's going to be bounded by this envelope of exponential functions. So this is kind of like e to the 3/4 over t, and then it will oscillate back and forth between these things. So the solution grows as t goes to infinity. And that's not physically realistic. We can't expect things to grow forever and ever and ever as we go on. So this kind of gets you the final piece of the puzzle for a second order DE. Once you understand about complex exponentials, you can write things in that form, but more realistically in terms of sines and cosines will then allow you to solve any second order DE.